in our segment routing module, so what first we'll start with the recap of the MPLS, and in this recap, basically the objective that we'll see is how basically a traditional IP routing was happening, taking as an example of 3 routers, and then we'll see how the IP routing, how route table lookup happened, and then when we introduce BGP in that, how the routing for BGP will be taken place, and then we'll see that how BGP resolve its next hop and what is recursive lookup and all. We'll discuss that, and what is BGP-free core, how we can create a BGP-free core and use MPLS. Also, we'll see that the traffic tagging with MPLS labels, and how label switch path is created and which all protocols are being used in this label switch path. This is basically an MPLS recap that before we start segment routing, we will able to just recap all these concepts. The prerequisite for this is basically you should know about link state routing protocols, you should know about BGP, you should know about label distribution protocol and RSVP and the difference between them, why they are being used in MPLS. So in this topology, we will have router 1 with loopback 1.1.1.1, router 2 with loopback 2.2.2, and router 3 with loopback 3.3.3, and these are the link addresses, right? And for example, we have configured OSPF between them. Here and here we'll have already OSPF is there. So OSPF is a link state routing protocol. So we need to enable OSPF in the interface, and based on the interface, it will able to discover its neighbor, and then your OSPF will come up. So once your OSPF is there, so OSPF is a link state routing protocol. So each and every router will have the information about all the routers. For example, if you see R1 database or R1 route table, so you will have a loopback address. It will be there in R1. Similarly for R2 as well. And similarly, these are all this is basically a connected route, and these are learned from OSPF as well, the leak routes. Now, for example, from a R1 perspective, when I want to reach, for example, if I do a ping, and if I do ping for 3.3.3.3, so what will happen in this case? So when I do a ping, so when I do initiate a ping from R1, so what will happen? It will check in the routing table. So in your routing table, it will check what is the destination 3.3.3.3. Based on this destination, it will check, okay, this is learned from OSPF. And then it will check what is the physical next hop that the packet will exit from this device, right? For example, I have another interface here pointing to, let's say, R4, right? And then we will have that connected to R2, and then it's going to R3. And then OSPF will also advertise this 4.4.4 as well. But as for OSPF algorithm, it will choose the shortest path, and based on the shortest path, it will tell you that which is your exit next hop. For example, I have a cost of 10, here I have a cost of 10, right? So what will happen is, so this is the shortest path in order to reach 3.3.3.3. So it will give us the shortest path to reach R3, and based on this shortest path, how the packet that has been there, which is a ping request, how the packet will exit from this device. Either it will go through this or this, right? So based on your shortest path, based on your route table, it will tell you what is the physical next hop. And the physical next hop will be pointing as 10.1.1.2, which is directly connected. And then it will reach to R2. And then from R2 to directly it will go to R3, right? So basically what will happen, a packet in ingressing, for example, R3 packet, for example, you initiate a packet here. The packet will egress from this interface, from how it will come to know about this interface, from the routing table, and it will reach R2, and then it will reach to the destination. So this is what basically a plain IP routing is happening. Only the IP packet routing is happening. This here, it will check the destination address of the packet, and then it will move forward. And then at the destination, it will check the route table and then say, okay, this is what the packet is destined for. So when we talk about BGP is basically different, right? So for example, OSPF, we need to have the adjacency between the two devices, directly connected devices. But in case of BGP, so basically we can have an adjacency from R1 iBGP from R1 to R4 all the way, and then eBGP between the two different autonomous systems. So if you see here, we have an autonomous system 65351 here, and then we have another autonomous system 65350, right? So for example, here what happened is we advertise a route that is, let's say 172.16.1.1. So this route, let's say this route, this R1 is connected with, and then it advertised to eBGP. So for eBGP, it will advertise, right? And then it reach here based on whenever it advertises a route, it will have a next hop attribute attached to that route and the autonomous system as well, right? So once we have that route here, so what will happen? The route R4 will also advertise. So any eBGP learned route will advertise to iBGP. Right, so the route will be advertised, and then for example here iBGP, we did a next hop self configuration over here, and then based on this next hop self, it will advertise and will get the route as 172.16.1.1 with a next hop of, for example, next hop is 4.4.4.4, which is R4, right? So next hop 4.4.4.4. The route is 172.16.1.1. For example, R1 wants to reach to R5's this 172.16.1.1. So what will happen here? So BGP, in this case, this is a route learned from protocol BGP. Right? Earlier, this route, this 3.3.3 was learned from protocol OSPF, because we have OSPF here, right? So now it basically, BGP is a protocol which advertised this one. And then BGP, whenever advertise this, it advertise with a protocol next hop. So when protocol next hop is there, so basically what this router will do, it will check in the routing table first. And based on this routing table, it will come to know, okay, this is what learned from BGP. And it will also check the, okay, this is the next hop. So what it will do is R1 will do a lookup for 4.4.4.4 as well, right? Once it will check the destination address, because we want to reach here. So it will check the next hop. Based on this next hop, again R1 will do a recursive lookup, route lookup for 4.4.4.4. This 4.4.4.4 should be there in your routing table learned via IGP. So if we have OSPF or ISIS in this, it should learn from an IGP. The reason is, the question again, how the packet will go out from this device, right? So it will go out from this device by, so it will go out from this interface because of the shortest path, because IGP relies on the shortest path of it. So then packet will reach here, right? So IGP, we did a recursive lookup, and based on this recursive lookup, basically we found that 4.4.4.4 is learned through IGP. Let's say IGP as OSPF, and packet reach over here. At R2, we'll do again the destination lookup, because this is a unicast packet. We'll do a destination lookup. What is the destination address? Destination address is 172.16.1.1. We'll do a destination lookup over here, and then we'll see that this IP address is not there in the routing table, right? What will happen? Packet will drop, because this IP address 172.16.1.1 only aware by this router and this router. R2 and R3 are purely based on the IGP routers, just providing an underlay perspective. So we do not have this route to be advertised to these devices. If packet coming in, then packet will drop here. Simply it will get dropped because it's not there in the routing table. What we'll do with next? So in order to resolve this problem, so basically we need to have, either we'll go with full mesh BGP, or we can leverage route reflector, or we can have configuration config. So why? Because, for example, again the same example, from here I'm advertising a route 172.16.1.1. So this route advertised by eBGP, and then based on the previous case, we received this route 172.16.1.1, and based on this, the next hop is R4 4.4.4.4, and we do a recursive lookup, resolve it, packet sent to R2. R2 do not have this destination address. In order to R1 to send the packet to R5, every router should have this information, this destination IP, then only it will work. Full mesh, if we have full mesh BGP, then each and every router will have this one. Or if we have a route reflector, so for example, this will advertise a router to the route reflector will reflect the route to each and every device. So as a result, now for example, this route 172.16.1.1 next hop 4.4.4 will be here, as well as 172.16.1.1 will be here, 172.16.1.1 will be here, and here as well, because we already received that from eBGP. And then what will be the next hop? Next hop for every router, whatever router reflector is reflecting, it will not change the next hop by default. So the next hop is 4.4.4.4. In the data plane, so when the packet comes here, so same thing, it will check the destination address here, do a recursive lookup for this. In the IGP table, it will check, and then exit interface, reach here. R2 will check the routing table. Okay, routing table, we have this route. Do a recursive lookup. Okay, how to reach 4.4.4? It will go from this. R3, packet received, it will check the destination address in the routing table. Okay, then how it will go out from the device? Recursive lookup for R4.4.4.4. It will say that, okay, this is the next hop to reach, and then it will reach here, R4, and then R4 will send it to R5. So this is how the packet data plane packet flow will be. And then learning of the based on the control plane learning, your data plane packet flow will be done. Looking at this topology, this is for a single destination that we are talking about, right? So for example, if it's a entire internet routing table, right, and then we want to reach to everyone, and okay, transit routers or edge routers, we will be able to understand, okay, we need those routes. Those routers should be capable enough to do that. But the core routers in your network, right? Why should you have at the entire routing table of the internet, millions of route in each and every devices? It is not required, because it is not required in terms of the design perspective, as well as, for example, you need to spend a lot of money in order to have R2, for example, in this case, R2 and R3, in order to have the store this route, all entire routing table in your route R2 and R3. Basically, you need to spend a lot of money in order to get those type of hardwares, and based on that, it will able to carry those information or routes. Full routing table. So basically, in this type of scenario where we do not require any kind of any similar to an entire routing table, it's not required at all. Still, we can work. So we need to find a solution in terms of how our core should be free from BGP. So there comes the problem which is solved is what? Solved by MPLS. In this scenario, taking this scenario under consideration, we do not need the entire routing table to be there in these two devices. So we need a solution in which we say that BGP free core, right? So BGP, how will achieve a BGP free core? We need some protocol to address this. Along with IGP, it is not possible. So we need some protocol to address this, and that is being addressed by MPLS. Okay. So basically, in order to build a BGP free core, we need a protocol that will help us in order to free from BGP routes for these core devices. So rather than running BGP in this core device, we will run something else that will prevent us for getting the packet to drop. For example, in our case, 172.16.1.1 was there. It will advertise to this, R4 advertise to R1, and then we will have 172.16.1.1 here with the next hop of 4.4.4.4. So what will happen here? So what was the problem? So packet, do a recursive, so packet destination lookup, do a recursive lookup for this, packet traversing, reach to R2, check the destination address. Its destination address is not there, so it will get dropped. So in order to resolve this, we will have route reflector, full mesh BGP or config, right? So every core device should learn the BGP route, but that is not required. So we need something BGP free core. How that will be solved? That will solve basically in order to have, we'll need to have a kind of encapsulation or a tunnel end to end. So tunnel between these core routers. So we should create a tunnel between these core route devices so that based on this tunnel, your data is coming. For example, you are sending a data and then you will have an IP packet. That IP packet destination is 172.16.1.1. The problem was exposing this packet to R2. If BGP is not there, then it is getting dropped. now we should have a mechanism in order to have an encapsulation. We should have an encapsulation, and so that if that encapsulation receives over here, so your IP packet will not get exposed to these core devices. For that, we will leverage MPLS. So MPLS is a data plane technology which will encapsulate your packet, your IP packet, with an MPLS header. This is your MPLS header. And then we will have, on top of that, we will have a Ethernet frame. So when we have MPLS in this, so basically these routers, the core routers, acting as just doing an MPLS label lookup and performing a push and pop operation, push, pop and swap operation, so that your IP packet will remain encapsulated in these devices. As a result, if R1 wants to reach to the customer route via R5, then it will go via this packet, will get encapsulated with MPLS labels. Swap will happen here, packet traversing with that. Again, it will check the label, do a swap, and then it will reach over here. And then when it will reach over here with an IP packet and a data and an IP packet, so basically R4 will have that 172.16.1.1 route in the routing table, because it is learned through eBGP, and then it will send that, it will route that packet towards R5. So MPLS will help us for a BGP-free core. This solves the problem. For example, if we have an internet routing table over here, we can have, because this is a transit device, we can have, this is an edge device, transit device. Those transit devices will have the capability, but core routers do not require that kind of hardware in order to support those many routes. So indeed, we need to have a technology, and that technology is something which is called as MPLS. And MPLS we need an MPLS for this kind of scenario. Think about a big service provider, right? Where we have the internet facing and all. So that there we are required this MPLS technology in order to save the core. So that is what BGP-free core. Core device do not require any BGP routes, only MPLS encapsulation, and based on this core device, they will do these operations. So let's take this example, right? So for example, I have again 172.16.1.1. This is advertised via eBGP to this R4. R4 advertised to R1, 172.16.1.1. Next hop is 4.4.4.4. This is my MPLS core, and then it advertised via eBGP again, 172.16.1.1. And the next hop is this one, right? Anything will be eBGP next hop. So what will happen here is the packet R1, let's say this is R6. R6 will initiate the packet. So the packet will look like this. So the frame with R1 as a destination MAC address, this R6 as a source MAC address. Source address is this R6, and then destination address is 172.16.1.1, this one, right? Packet reach to R1. At R1, this packet will reach to R1. So what will happen in R1? It will do a route table lookup. So when it will do a route table lookup, it will do a lookup for destination address 172.16.1.1. 172.16.1.1 is already there, which is learned from BGP. What is the next hop? 4.4.4.4. Now, based on this next hop, earlier when we have an IGP core, this next hop was getting resolved via IGP to find the exit next hop, right? How the packet will go out from this route. In case of MPLS, the next hop resolution will be done as well, but it will check now. It will check the label. I need to have a label for this next hop. Okay, we should have a label, and based on this label, it will do. And that label is basically learned through your LDP or RSVP or a segment routing and all, right? So it will check and that is basically underlay is your again IGP. So gives here how to reach 4.4.4 with a label. So why we need a label? Because from here onwards we are encapsulating the packet again, right? We are encapsulating the packet all the way till this. How we will encapsulate that packet? So that packet will get encapsulated with the help of the next hop. First do a next hop, and this next hop should have a label. So this label is nothing but a transport label in order to get through the core devices, and we will have an MPLS label imposed between the layer 2 and layer 3 header. So that is the reason why MPLS is called as layer 2.5. Now the packet will reach here. So once the packet will reach here, so only we are doing a label swap operation. You just see that change R2 is the Ethernet header, because every segment will change the Ethernet, right? MPLS will get swapped with a label. But if you see that your IP packet is remain encapsulated. As a result, this will reach here, will do a label swap operation, and then it will do a PHP, and then plain again the same kind of IP packet will reach over to R4. Because R4 knows about 172.16.1.1 because it's learned from eBGP, and the next hop is basically this, and then it will send that packet towards R5. Once R5 receives, the operation, end-to-end operation has been done, right? So what makes here, basically using MPLS technology, we can achieve a BGP free core path, and we save a lot of money in order to have not to expose the entire routing table in all these core devices. So for this, from here all the way to this is what this is referred to as the tunnel that is referred to as a label switch path, right? So we will have a label switch path all the way from R1 to R4, and this label switch path is created by label distribution protocol, LDP, RSVP, and also segment routing as well. So we'll see segment routing in detail from our after this module. We are going through MPLS recap, so that we'll see that okay, now if it is LDP is distributing the labels, RSVP creating an LSP path end to end, and then distributing the labels for that. Hope this is clear based on the entire MPLS recap chapter. This device are basically called as ingress device or provider as devices. This is called as egress device, egress P. This device is basically called as P devices, provider devices, right? And MPLS, as we know that MPLS, we are doing a push pop operation, push at the P device, swap operation between the R2 and R3. When we are sending to R2 to R3, we are doing we swap, we check the label, and then we do a swap operation. Your IP remain intact end to end, so no lookup for IP over here. These two devices, P devices, do not have any kind of IP lookups. There is another concept as well. We will have an implicit null. This is a reserved label for implicit null. Implicit null is label value 3. So where when R3 is going to send the packet to R4, basically do a PHP, an ultimate hop popping. So only the IP packet will reach over to R4. Where we'll have something called as explicit null as well. So explicit null is nothing but label value 0. So label value 0 is being used if we do not want. So default is PHP in any of the device. So if we do not want PHP, if we do not want to expose the IP or the header, whatever the inside IPv6 or IP, whatever is there inside, we do not want to expose, then we will go with explicit null value, which is label value of 0. And then we will have a router alert bit as well. So router alert is label value of 1. So that is, we'll have a different use cases for that. So implicit null for the PHP. If we do not want PHP, we'll go with the explicit null. So coming back to the first slide. So basically what we discussed so far, IP routing using OSPF or ISIS, how the IP routing will be based on pure IPv4 packet. Based on that, it will check the routing table based on the destination IP of the IP packet. So BGP is different than OSPF and ISIS. So we can create end-to-end IBGP, like adjacencies, OSPF and ISIS. We need to have adjacent, means neighboring devices to create. In order to have, so BGP protocol next hop will be resolved. If it is a IP routing only, it will resolve by IG. If it is MPLS based, it will resolve using a label which is given by LDP, RSVP, or segment routing. We have a problem with full mesh BGP, so that we cannot distribute BGP routes in all the core devices. So we need something BGP core free, right? Free core path. So based on that, we will have a technology which is MPLS, which will help us in order to encapsulate the packet end to end, so that the core devices especially do not require any BGP routes in that. And then based on the traffic, we will have a label, that is which called as MPLS label, which will get encapsulated in between an IP and Ethernet header, and then that label is basically referred to as 2.5 layer. And when we talk about this, all the intermediate routers, those are able to understand the label, they will perform a push and pull operation. How label switch path is created? Label switch path is basically created for this chapter. RSVP and LDP is used to create the labels, and MPLS is the data plane technology. And then we will have certain label values, which is, for example, implicit label is used for PHP. Explicit label, if we do not want PHP, then we should have a label 0. PHP is default. And then we will have another label value is router alert bit, which is RA bit, which is label value of 1. So this is what, just a recap for MPLS. And then next we'll start with the segment routing.